The concept of transfinite space-time is that both space and time are changing over time. You may be familiar with the phenomenon of time dilation, but what is proposed here is that time is also dilating over time in a transfinite way. Although time is always experienced a minute at a time, yesterday's minute was relatively faster than today, and tomorrow it will be that little bit slower. It is transfinite because this has always been the case, as time evolves from infinitely fast relative to now to infinitely slow in the distant future, adding another dimension to time. But what do I mean when I say time can be faster or slower? We now have clocks so accurate that we can see the difference between time upstairs in a house and downstairs. Because of gravitational time dilation, time will run slower on the ground floor of a building relative to time on the top floor. The difference is very small, but if we had identical twins and one lived on the top floor, say one lived on the ground floor, then the top floor twin would age faster. Now you may think it would be much better to live on the ground floor and age slower, but the truth is that they both age in the same way and may live the exact same amount of time, in which case top floor twin dies first. But if a disaster struck and both died at the same exact moment in time, the top floor twin would have lived a longer life. Like our measurement of a minute, light speed is always measured the same, and therefore it follows that if time is slowing down over time, so too is the speed of light, as it has to mirror the time in a transfinite way in order to measure a constant. The intention of this presentation is to demonstrate an observational difference between finite and the transfinite light speed scenarios. The measured constant speed of light is now used to calibrate our measuring rods. For instance, a meter is about 3/millionths of a light second. A light second would get us about this close to the moon, a light year about 6 trillion miles, and our nearest star, other than the Sun, is about 4¼ light years away. It became apparent that light was not instantaneous after astronomers, like Galileo, started using the movement of Jupiter's moons as a cosmic clock. Galileo was chasing the longitude prize and needed to measure time precisely. Although he invented the pendulum clock, it was then far too inaccurate for this purpose. Later, the astronomer Cassini noticed some discrepancies in the timing of Jupiter's moon, Io, suggesting that the inequality may be down to light having a finite velocity. Ole Romer and Christian Huygens would later calculate the first reasonable figure for the finite speed of light, carefully observing Io's orbit. The orbital period of a satellite, such as Io, as it orbits Jupiter, has a very consistent periodicity. But what we observe from Earth depends on whether Earth is moving away from Jupiter or towards Jupiter. When Earth leaves opposition, the orbit of Io appears to slow down as Earth's orbit takes us further away from opposition until we are at conjunction. Although we cannot see Jupiter at conjunction because the Sun is in the way, the light would take about an extra 22 minutes to reach us, or thereabouts. Then as we leave conjunction and head back towards opposition, Io's orbit appears to speed up and the delay reduces back to the original. This changing orbital time of Io as we move between the shorter distance at opposition and the longer distance at conjunction will give us a means by which to calculate the speed of light. The visual effect of Io's orbit slowing down was due to Earth moving away from Jupiter. This is a temporary situation, but for Voyager 1, the Jovian cosmic clock would always be losing time as the time delay for the light signal increases with distance. However, in the case of distant galaxies, their increasing recessional velocity would make our Jovian cosmic clock appear to go slower and slower. The Comoving effect is not only to lose time, but to lose time more rapidly. This poses an interesting question, because the linear increase in recessional velocity is without limit. At a far enough distance, the recessional velocity will go superluminal. The interface between luminal and superluminal is called the Hubble Sphere. Note that this is not our visible horizon. Now imagine that these three galaxies were identical to ours and had identical Jovian systems, and we were able to observe them all. Their cosmic clocks would appear to run slower as the recessional velocity increases with distance. Therefore, the closer system would appear to be orbiting faster than the next, more distant one. But what of the one past the Hubble Sphere? This galaxy on the Hubble Sphere will be receding at the speed of light. Would it not appear stationary? And therefore this one that is past the interface, should that not be going backwards in time, getting younger before our eyes like a film being played in reverse time order? If this is correct, the further away from the Hubble Sphere, the faster the reverse time order visual effect would be. Now that rather fantastical hypothesis of mine was based upon light having a finite velocity. However, having already concluded that time was faster in the past relative to the present, it dawned on me that for the speed of light to remain a constant measured speed, it would have to mirror the way time dilates over time, slowing down relative to the past. Now, although distant things were younger when they emitted their light, the further back in time we look, the resultant time and distance Comoving scale means that light was faster in the past relative to now, and so everything in our visible horizon can now be seen to have a forwards in time progression. The apparent expanding universe caused by a changing Comoving distance scale will still make distant events appear to progress slower through time, like our Jovian clock as we move away from Jupiter, but all those events will appear with a forwards in time order progression as the narrative of our universe unfolds in time. If, for instance, a second now is equivalent to 2 seconds when light left that galaxy on the Hubble Sphere, where the redshift is Z1, and 3 seconds pass on a galaxy where the redshift is Z2, then when the photons left the surface of last scattering at Z 1100, 18 hours pass for every second today, and although the speed of light would have been 186,000 miles per second back then, that would be equivalent to over 200 million miles per second today. Current theories put the recessional velocity down to the space between the galaxies and the galaxy clusters stretching. An analogy for this is to sew buttons on a piece of elastic to represent the galaxies and pull the elastic apart like this. Note that we do not just draw the galaxies on the elastic because the space they occupy does not stretch. The buttons move apart but remain fixed to the same spot on the elastic. By designating the left-hand button as the observer, we can see that the further away a distant galaxy is in relation to the observer, the faster that recessional velocity will be. Here we have a galaxy. The ruler represents our light speed measuring rod. If the speed of light is transfinite, slowing down relative to the past, then the light speed measuring rod will also be shrinking. Gravity-bound stars have a peculiar movement towards the center of the galaxy. In the fractal topology of space-time theory, all atoms are shrinking over time, so an observer will not notice this hidden peculiar motion as galaxies shrink. We will now add a couple of buttons, and instead of stretching the elastic, we will shrink the buttons and the ruler to replicate transfinite space-time. We get the same linear increase in the measured recessional velocity as before, but this time the buttons do not actually change their position to achieve the apparent recessional velocity. Just like in the standard model of cosmology, the apparent recessional velocity is homogeneous and isotropic to all observers. For instance, this observer. A now moment exists simultaneously across our universe, and we only observe the past, and we can only observe objects that shared the now moment at the genesis moment of our transfinite period of time. We can calculate how long ago light left a distant object by the redshift, but that age and distance is relative to our present time and distance scale. The redshift we observe at the Hubble Sphere is Z1 and represents an almost 14 billion light-year distance, but this is just a fraction of the observable universe where the light from the youngest matter has been redshifted into the microwave spectrum. Thank you for your interest, and I hope it has been food for your thoughts.